Good morning, good afternoon, and good evening. My name is Viral Vigela, and I'm the account manager for X-ray CT technology with Rigaku. I'm here with our co-presenters, Angela Criswell and Aya Takase.
Hi, everyone.
Thank you all for attending Rigaku's webinar series, Ask the Expert. The best way to learn something new is talking to an expert. Our series will cover various topics and will be joined by industry experts to help us better understand CT techniques. Today, we want to welcome Dr. Awen Autret as our expert. Awen is an R&D engineer with NOVITOM who helped design their simulation program for X-ray images. He'll be discussing how to optimize data acquisition parameters without having a CT scanner. But before we begin, a few housekeeping items. We'll be taking your questions live during the session and answering them, so please don't wait until the end to ask. As usual, please submit those questions via the Q&A button. We won't be monitoring the raised hand function, and we'll try to get through as many questions as we can during the webinar. And any unanswered questions will be responded to after the webinar is completed. If for whatever reason you have difficulty viewing this webinar, please note it is being recorded and we'll be able to give you the recording beginning tomorrow. With that being said, let me turn it over to Angela and Aya.
Thank you, Viral, and thank you very much, Awen, for joining us. I'm gonna stop sharing my screen so that you can share yours. Are you ready?
Yes.
Okay, so I'm gonna stop.
Can you see my screen? Okay, great. So first of all, I would like to thank the people at Rigaku for inviting me to present this webinar. I'm Awen Autret from NOVITOM, and I'm the software development manager here, and I'm the main developer of NOVISIM, the CT simulation software that we develop here.
Thank you. So this topic, this is the last episode of our series this year, but this topic is a little bit different. And Awen is going to talk about how we can simulate CT data. And some of you might not be very familiar with this concept, so I'm going to ask him on first. So Awen, can you briefly describe how you can simulate CT data?
Yeah, sure. Thank you for your question, Aya. So basically, the simulation workflow works this way. First, we simulate the spectrum of the X-ray source. So the spectrum is just a list of numbers that give the intensity of the X-rays at the different energies or wavelengths. So we have different mathematical models for the different types of source that you can find in lab CTs or synchrotron facilities. And then we take account of the various filters that can exist along the X-ray beam. So we'll attenuate different wavelengths with different amounts. So you have a new spectrum after the filters. And then based on the ray tracing approach, we compute the attenuation and the phase shift that the sample caused on the X-ray beam for all the different energies that we have in the spectrum. And from this point, we have what we call a wavefront, because the X-ray beam is an electromagnetic wave. So this wavefront will have at every point an intensity and phase shift that depends on everything that we calculated previously. So we propagate this wavefront using the Fresnel's diffraction equation on the detector plane. And based on the different efficiencies of the scintillator, the sensor, we can build the radiograph. And then we add the PSF and the noise, taking into account all the elements explained previously. So this uses multiple physical models that I won't present in detail here. So if you are interested, here are the references, and this will be available in the document that you will be able to download on Rigaku's website. And practically, in our software, simulation looks like that. So the first step is to import different objects in your simulation. It could be different components of a same object. You define the composition of these parts, and then you align them according to the X-ray beam. At this point, you will be able to see a radiograph, and then you can adjust the different parameters of your CT system, the voltage of the source, and add filters. And when you have adjusted everything, you can run your CT simulations. It will generate 1,000 of radiographs that you can then reconstruct in the software, and do your analysis. Try to see if you have the required image quality. So, do you have some question on this first topic?
We do have a question, Awen. First one is, if I wanted to use NOVITOM free trial, can I do it on my laptop, or do we need a specialized computer to run it?
So you don't need a specialized computer, because we use the analytical models. This is not too computationally intensive, so you can run it in your laptop, but yeah, compared to a workstation, you can't have like huge images. Limit yourself perhaps to 1,000 by 1,000 image, and if you want to do a reconstruction also, this is better if you have NVIDIA GPU, so you can run it on the GPU, because the CT reconstruction on the CPU it's really intensive, so it can take sometimes this step.
Got it. Thanks
No
for
more
that.
question?
That's good. Good.
Okay.
No, the regular computer can do that, so that's a good thing, at least the initial trial.
Yeah.
All right, so the next question is for you, the audience. So I'm going to launch our first poll question. And what we'd like to know is, what is your field of interest? Are you in the automotive aerospace, biology, medical? Perhaps you're in pharmaceutical, chemical, or maybe something else entirely. So we've got about 30% of all of you answering so far. So we'll give another few seconds. Yeah, it's kind of pretty balanced. A lot of others though. All right, so 3 more seconds, 2 and 1. I'm going to end the poll now, and I'm going to share the results with all of you. So about half of you are in the other, and 30% automotive, aerospace, close to 10% biology, medical, and almost 20% pharma, chemical. So I'll stop sharing and send it back.
So, okay, perhaps we have people from the CT manufacturer side.
I have a feeling.
Perhaps so.
But yeah, it's pretty balanced. Yeah, currently I think the automotive and aerospace and the medical fields are those where we find a lot of CT users. But yeah, this is yeah, more and more used in every field of the industry.
And before the webinar started, we were just talking about the battery industry as another big one growing.
Yeah, and additive manufacturing as well. Big market.
Yeah, that's
there,
another
too.
good one.
Hey, I want to, before we start the next question,
Okay.
I was having a hard time copying all the links on that you were sharing, but I'm gonna add that to the chat here just for our audiences so they
Okay.
can look at it. So it's there in the chat window, guys.
Thank you. Okay, so thank you, Awen, for explaining how you can simulate the CT data. When you have a CT scanner in your lab, we kind of take the whole process, for granted. It's easy to walk into the lab and just run a measurement. But I can see that there are a lot of factors you need to consider when you actually simulate CT data. Now, knowing that it's quite a bit of work to simulate the data, at least physics-wise, I want to ask the next question. So who uses NOVITOM's tools, and how are they benefiting from the simulation capability?
Thank you for the question. So depending on the applications, there are different kind of users. So I will present the different applications of the software, at least the more common ones, and who is interested in this application. So this tool is useful to evaluate the feasibility of a CT study, or also evaluate the limits of this study. And how you can do that is you import your model, you run basically the acquisition that you will do for this study, and add some virtual defects to your object, and you see if it's a feasibility, if your measurement is possible at all, or if you want to evaluate the limits, you can then do the analysis on your data, and knowing what you put in the simulation, you can compute the errors, and for the different size of spheres, for example, you can do a radius measurement and have an error associated for each different size. So this interests mostly the people that are using CTs, so companies and institutions that use such tool. And these people are also interested in this application, which is a setup optimization. When you use a CT, you can't always know in advance how to set up your machine, how to place your sample in the field of view. There's always some adjustments during the experiments, and this can cost time and money, because those equipment are expensive. So here is an example where we search an orientation that was minimizing the attenuation, and you can also try to find a setup that allows you to detect the defects that you want to detect in the least amount of time. So you can tweak all the parameters, and then when you come to your experiment, you have more information in your hands. And another application is to train people to the X-rays and the CT techniques. So you can do practical works with the software, where you give to the students an access to the software, so they can play with the different parameters and better understand how the radiographs forms. And then you can go to the next step and explain how CT works, or the acquisition of all the radiographs, and how the reconstruction also works. And you can also show them multiple acquisition parameters, or leave them and the students play with the parameters to see how they affect the the final CT image. So this is mostly for training institutions or companies that are training people to use CT. And this could be also a tool to generate image databases, because you can run a script that will generate thousands of simulations, and then these databases could be used to train a neural network for certain tasks. So in this example, it's to correct an image artifact that you could have in CT images. So those are the applications of CT simulation software. So if you have some question on this topic.
Yeah, you mentioned obviously hardware being expensive, and simulation does help in cost saving side of things. Do you guys do sort of contract testing service to simulate a set of data for machine learning for educational institution, or do you need to purchase a NOVITOM license to do it yourself? Or if you can talk about that.
Yeah. So NOVITOM is a service company in the first place. So as a service company, we can for sure do that. This is not something that we have already done. We had some contracts where we used NOVISIM mostly to evaluate the limits of the system. But this is something that we can do also. If you want to upgrade your database later, perhaps it's better also to have a NOVISIM license. And this is something else.
So it's a good way to get it out and just have you guys take a look at it and see what you find out for a user or academic institution if they want to get a few images tested and see how it looks on your network. Yeah.
Yeah.
Awesome. Thank you.
All right, so the next question is again for you, the audience. I'm going to launch our poll question number 2. And the question for you is, which use of CT simulations is the most relevant to you? Do you see benefits for training, acquisition, optimization, evaluating perhaps detection limits, or maybe building databases? I see opportunities for all of it, really. So for sure. We've got about 30% of our attendees responding. So we'll just give a few more seconds to let everyone have a chance to vote here.
Pretty evenly distributed among the 4 choices so far.
For sure. All right. Only half of you have participated so far, but we can't wait forever. So I'm just going to give a couple more seconds, and now I'm going to go ahead and close this poll, and I'm going to share the results with each of you. So for the most part, it's balanced between the benefits of training and building databases. For sure, that's good use, with acquisition and evaluating detection limits to a lesser degree. So I'll stop sharing and send it back to you guys.
Okay, so on our side, we are using it for all of these applications, but historically we used it mostly for feasibility and evaluating the detection limits. But more and more people are interested in this tool to generate databases. So seeing this one in the top 2 is not so surprising.
I guess if you run a contract service lab, I think a feasibility test can be a very useful tool, because you don't need to actually receive your client samples to see if the scan is going to work out.
Yeah, sure.
Yeah. Okay. So the next one is going back to the presenter. So in examples of where people use CT simulation, you've mentioned measurement condition optimization. So the next thing I wanted to ask you on is how can you exactly use simulations to optimize measurement conditions?
Okay, so to optimize the measurement conditions, what you can do is first of all look at the radiographs. Usually we have some guidelines that tells us what is the minimal transmission that you should have, or what is the intensity in the flat field. So you can use those guidelines to try to get a radio that follows those. So here, an example, you have a transmission which is too low. So you, let's say, add filters, and then the signal to noise is too low, or your counts in the flat field are too low, so you increase the exposure time. So this is really simplified because you have a lot of parameters that you can tweak also, but this is a possible way to optimize just these two parameters. So, and then you can go to the tomography slices, and if you have to do an analysis on the tomography on the tomography reconstruction, you can run the full simulation, reconstruct the volume, and try to do your analysis. And depending on what you think is limiting your analysis, for example, here you think the beam hardening and the streaks are an issue. You can change some parameters, add filters, and here you have less beam hardening, no streaks, but still the beam hardening is too strong and it's too noisy. You tweak some more parameters, and then you are happy with your configuration. So this is also an iterative process. So, and we have many parameters to optimize, but yes, you can work first on the radiographs and then on the tomography slices. This is how we do it, how people are doing it currently.
Great. I was wondering, Awen, do you have a way to automate this process? I know it's a pretty simplified process from scan parameter optimization point of view, but can we automate this, or do you already have it automated?
So we don't have something automated right now. We are working on this topic. So this could be quite complicated because if you do an automatic optimization, you need a cost function to optimize. And there is no like universal cost function that will work for everything. Sometimes you can live with some beam hardening or more noise, but sometimes they prevent you to do any analysis. So this is complicated. But what we are developing right now is, I think, a good first step is we let the user define some region of interest to measure the noise and the contrast, and then the simulation will iterate to find the configuration that will meet these requirements. So this is still under development, but we are working on this this way of optimizing the parameters.
Gotcha. Thank you.
If this process can be somewhat automated, I think a lot of people can benefit from it.
Will be a
Because
game.
we get questions from our customers and the users about what to do to improve the data quality. Because they look at the data and they know that I don't like this, but I don't know which parameter to change to make it look better. So if the software can tell people how to do it, that would be great.
Yes, we we hope to have something that that helps the perhaps non-expert user of tomography, but also the expert sometimes could be quite difficult to find the perfect setup.
Yeah, you can see the challenges of that. That's why it's user defined right now, and hopefully in a near future it changes and gets a lot less, less user defined, more automated, and machine learning on its own.
Okay.
Okay.
Right, so one more poll question for you, the audience. This happens to be our last poll question for this presentation. I'll launch it now. And the question is, what is the primary challenge you encounter when using CT scanning? Are you challenged by defining the optimal setup, or perhaps with dealing with your particular system's limitations? Or are you challenged by post-processing the data, or perhaps something else? So give everyone a chance to respond. I know often when I'm trying to optimize a setup, it's how many different settings are you going to try and to get the optimal data? So you only have a limited amount of time for sure. So that's definitely one I can understand for sure. So we have about half the people have answered so far. We'll give another 3 seconds, and I will end this poll and share the results. And it turns out that it's balanced most heavily with those top 3: defining the setup, dealing with the system limitations, and also post-processing the data. So I'll stop sharing and send it back to you guys.
Okay, so everyone struggles with the CT system. So I think we really need this automatic optimization to help people to achieve the best image quality, and perhaps struggle less with the system limitations also.
For sure.
Interesting.
Before we move on to the next question, we just had a question come in from the audience. We're showing different scan objects. Do we need an initial scan of the object to perform the simulation, or what initial data do you use for the simulation?
So you don't need an initial scan to do a simulation. You need to know the information on your CT scan. So for the source, you should take a look at the datasheet perhaps to know the anode compound, but it should be a tungsten most of the time, or to know the angle of the anode. Those are not so critical parameters. So I think on the source size, it's not so important to know exactly the parameters of your CT scan, and perhaps it's more on the detector size. You should take a look also at the datasheet to know which scintillator is used in it, what is its thickness, and what are the different parameters of the light sensor behind, so the quantum efficiencies, things like that. But you basically need the datasheets of your system.
So
So
for the
basically-
sample, I'm sorry. For the sample, if you were to simulate something for feasibility test or measurement, condition optimization, you can use I guess approximation of your sample as a CAD model or something.
So for the sample part, if you have STL or a mesh file of the sample, so this is the best that you can have. But if you can't have that, yes, you can try to recreate a sample which has a similar shape, roughly a similar shape. This should create the same artifacts. Most of the time, the artifacts are not extremely sensitive to the exact geometry of your sample, so you can roughly recreate the shape of the sample using basic bricks that you can have access to in the simulation.
And I remember that in NOVITOM, the tool, you have simple shapes like a cubes and spheres, so you can combine to approximate the shape of the sample.
You can do that, use these simple shapes to try to recreate something roughly similar.
So you don't need a sample, you don't need a CT scanner to create a CT scan.
Just the basic parameters, and you can get
Mhm.
the results. Yeah, that's interesting. Yeah.
Do you
All
have
right.
other questions, or we move on?
I think we
Yeah,
can move on.
let's. Mhm.
Okay.
Okay. So another area that you mentioned, where simulation can be useful was the training data. And this is the one that actually I'm mostly interested in. So can you use the simulations to create training data for machine learning? And if you can, how exactly do you do it?
Okay, so great question, and this is a topic that we are actively working on at NOVITOM. So we think this is possible, and I will show you some examples to convince you. So the first one is perhaps the simplest one to do. It's quite a straightforward approach that we took here. It was to reduce the noise in the images. And the neural network that we use is a UNet, and we built a training database with pairs of images. So one image had a noise, and another one had no noise, because this is a setting that you can set in NOVITOM. You can disable the noise. So we wrote a script to generate thousands of images with and without noise, and we trained the neural network on that. So here I will show you a result of what we obtained. So this is a concrete sample where you see the grains of sand and air bubbles. And on the top, this is the original image, and on the bottom, the corrected one. And if you look, for example, here, where you have small grains that are really hard to see in this image with all the noise, it's a lot easier in this image. You can see a lot of details. So I think this is already an interesting result that we obtain here. And we also use this approach, this really straightforward approach to correct the beam hardening. We generated images with beam hardening, which appears by itself in NOVITOM because we simulate a polychromatic X-ray beam. And we also did simulations with a monochromatic beam to have the ground truth images. So on the right here, and those are test images. So the original images, what we obtained after correction, and the ground truth. So you can see the beam hardening in the air is quite well reduced, and in the object it's not perfect, but already an improved image. And we tried this on real image also this time. So this one has a lot of beam hardening, but this is you can see in the air it's more homogeneous. I think it's saturated, but this is if we were able to see it's more homogeneous, and in the sample it's also more homogeneous, but sometimes it's a little bit too homogeneous. Here, for example, there is a phase which is a little bit lighter, should be a lighter gray than this one, so it disappears a little bit. So this is a tool that we use sometimes, but you have to be aware that this one has some limitations. We are still working on it. And another last application is the correction of the ring artifacts. So this approach uses this algorithm. So you do polar transform, so Bell operator. Then we use 2D units to extract the signal of the rings. And after an inverse polar transformation, we have an image with only the rings that we subtract from the original image to correct the rings. So here is a result also on this concrete sample. So as you can see in the bottom, most of the rings are corrected. You have really slight shadows of rings, for example, here, or a little bit here, but it's quite hard to see remaining rings here. So this artifacts correction are not here just to make nicer looking images. They are mostly to improve the results of the analysis. So I will show you some simple examples of how we can improve here as the segmentations of the images. This is the sample is a coil of platinum, which creates lots of beam hardening, lots of artifacts. And when we segmented it, we had a lot of small bad classifications. And after the correction, the image is not perfect, but the segmentation is quite a lot improved, at least. And here is an example where we corrected the rings. So if you do the segmentation on this image, you can see the structure of the rings. So there's a lot of noise also, but this was not an issue here. And after correction, the segmentation, you don't have these rings visible anymore. And the last example is a reduction of the noise. This was a sample, really low contrast sample. So when you adjust the contrast, you have a lot of noise, and the segmentation is quite difficult. So after noise reduction with our network, it's a lot more usable to do analysis on this image. Do you have some question on this subject, Vera?
Yeah, there is a question that came in. This is incredible with the AI corrected images. It's so much sharper than the original image. The question here is, how general or specific are the training results to the simulated data set? And can you apply trained network to a new data collected with voxel size, X-ray energy, different from what was the original training data?
So yeah, this is a really good question, and actually it's quite difficult to respond right now, because we don't completely know yet if the trained networks are really versatile and can be applied to a lot of different kind of data. So it looks like for the noise the noise reduction model, that it is quite versatile. We use it on data that I think you don't really find in the training database, because we are applying it on most of our images. So this one is quite versatile. The ring correction is also quite versatile. But for the beam hardening, sometimes it works well, sometimes it removes some structures, or as you saw. And so this is not something that you can respond universally, say it will be this will work on all images or it won't work. It's still a bit difficult to know when this will work well sometimes.
So it's a constant work in progress as you continue to train the data set and build the data set. Yep.
Mm-hmm. Do you have more questions here, or do I move on?
Move on to the next slide.
Okay.
Lightning round.
So now that brings us to the lightning round. So we want to change the pace a little bit and ask on Awen some, not necessarily CT simulation related, I guess, more personal questions so we can get to know him better. So we pretty much asked the same question to everybody, but where did you go to school?
So I'm from Brittany, so I did my scholarity up to the engineering school. I did all this scholarity in Brittany, but then I moved. So Brittany is the peninsula on the west coast of France, and then I moved on the other side of the country, near the German border, to do my engineering school, and I moved back to Brittany to do my PhD, and then I moved back to the east of France, in Grenoble, where I am now. So this is
Kind of went back and forth.
Yeah, west, east.
So you mentioned the engineering, but within engineering, how did you get into this particular field?
So yeah, when I was in engineering school during my last year internship, I worked for a company, a CT manufacturer company, so RX Solutions, and I discovered CT here, and then I continued to work on the tomography field during my PhD, which wasn't on X-ray CT but on positron emission tomography, which is a medical imaging technique. And after a few postdoc contrast, I moved to NOVITOM to go back to X-ray CT.
I see. So that's the field you're in right now. But if it wasn't that, I wonder what would that have been. So what did you want to be when you were a kid?
Yeah, when I was a kid, I didn't really have a plan. I didn't have didn't know, want to be like an astronaut, or I don't know. I was just really interested in nature, astrophysics, and the plants, the animals. This were the fields that attracted me when I was a child. So I studied in quite a general. I did quite a general study, and when I discovered CT, I felt that it was like at the intersection of many interesting fields, and this is something that I like about this field. You have a physics, computer science, and mathematics.
That's certainly true.
CT tends to do that to people. I've learned over the last few months.
So sounds like you found the right job for you. What is the part you enjoyed the most about your work?
So what I really like at NOVITOM is that we are using quite advanced tools like the synchrotron, and those tools are really fascinating, and being able to go there and to use them, it's something I really like. As I said, also being involved in all those fields through tomography, but also through our customers, which are basically in all the industrial fields that you can imagine. It's really interesting to see all this R&D everywhere. And another point that I like is NOVITOM being a small company, I can directly see the use of my work. So I develop the city reconstruction at NOVITOM and some image processing tools, and I see my colleagues processing the data for the customers with these tools. So this is something that really motivates me also.
I can certainly understand that. So this is the last question in the lightning round. So from your point of view, what kind of let's say new challenges or developments in the CT industry do you think we will see in the next 10 years?
So one challenge that we will face is the challenge that will be caused by the amount of data that we will have to process, because the CT systems are getting more and more sensitive, faster and faster, and the image size tends to increase. So the amount of data generated by those systems is getting exponentially bigger. And if we are already struggling with that, and it's not going to improve, I think, and we'll have to come up with some tools to automate more tasks to cope with this amount of data. So this is one challenge that we'll face, I think. And another development that I think we'll have in a city, I think we'll have phase contrast imaging more available on lab cities. So right now you have the gratings phase contrast, which is available in some lab cities, but this is quite niche, I think, for now. But this will be more and more used, especially as the development of spectral imaging will solve the mathematical issue we still have. I think when they solve those issues, we'll see more lab cities with phase contrast imaging.
That should be exciting.
That'll be nice. Yeah.
Yeah. And I totally agree with you about the data size. It's not 10 years from now, it's already a problem. Okay, well, thank you for answering a little bit, I guess, invasive questions. So I got not too much. But let's get back to CT simulation discussions. And we have two more questions. So one of them is about the experiments and the simulations. So far, you've shown us a lot of simulated CT images and radiographs, and I cannot tell the difference. If you tell me that those are actual measurement data, then I probably wouldn't believe you. You know, that's how real they look. So I wanted to ask you to kind of explain how well simulations and experiments match.
So this is a good question, and we are working also on this topic to make sure that what we generate is realistic. So the first point that we validate in our simulation is the spectrum that we generate at the beginning, and to do so we did some measurements on lab cities. So here are just two examples of some measurements that we did, and we have some small discrepancies below about 10 keV, but above that the spectrums are really good. And the agreement is really good between the measurement of the simulated spectrums. Another point that we look frequently is just by eye that what we simulate looks like at least the thing that we acquire on the synchrotron for us. But here it's an example of studies that we did on this is the coil of platinum that you saw previously. So on the top, you have the simulation. The bottom, you have the image acquired on BM18 beamline at the European Cyclotron Radiation Facility. And we are also doing more quantitative measurements. So I will show you some of those results. To do these measurements, we use staircase phantoms. So one on aluminium and one in PMMA. The result here for the PMMA sample. You have the images here. We are comparing NOVITOM images with the real images, and we are also simulating the same radiographs using a Monte Carlo simulation, which is the gold standard for X-ray with matter interaction simulation. It takes a lot more time, but this is a gold standard. We use it also in our validation study, and here are the results. So it fits quite well. And this is for the PMMA. The same result for the aluminium. We have a similar result. There are some discrepancies, but globally, this is a really a good agreement for both images. And as I said at the beginning, we are also simulating the phase contrast, so the propagation phase contrast in NOVITOM. And this is what generates these bright fringes in the border of the sample, which is here a wire, an aluminium wire here, and PEEK wire. PEEK is a kind of plastic. And here are the profiles. These are many profiles that are averaged. We did a registration to take account of the sample being straight. And you can see that the fringes match quite well also. So to validate the propagation phase contrast. You have some question, Viral, on this part?
Yeah, I guess the question here is, obviously it's pretty incredible how close we can get with experimental data and simulation. The question here is, why is NOVITOM's calculation faster than Monte Carlo simulation? And I guess if you can point out any key differences in that.
Yeah, so NOVITOM simulation is based on analytical models. So basically, you have one equation that you compute and you get your radiographs. It is really oversimplified, but this can be summarized like that. And Monte Carlo simulation, to build an image, you have to actually simulate the life of billions and billions of photons. So emitted from the source, they will hit the object, and eventually, after some scattering or not, hit the detector. This is why this is a lot more computationally intensive to run a Monte Carlo simulation.
Gotcha. Okay.
You have more? Yeah.
I was just curious about that, so that's cool. Okay.
Okay.
Thank you.
So that brings us to the last question for this episode. What is the future of CT simulation?
So on our side, the future is first of all the improvement of the speed of the simulation in NOVITOM, mainly using GPUs, which are not currently used for the simulation. They are used for the reconstruction, but not on the simulation side right now. And then the other development, which will be available in the next version of the NOVITOM before the end of the year, and it's the scatter simulation. So currently, NOVITOM assumes that the photon travel in a straight line, so they are absorbed or they are transmitted, but they can't be they can't change direction. And we are currently working on a hybrid system which will use Monte Carlo simulation on GPU to compute the scatter signal and continue to use the analytical model for the unscattered signal and merge them together. So this should allow us to have a fast simulation, but still an accurate scatter signal estimation. And the other point we are working on, as mentioned previously, is the automatic optimization of the acquisition setup. And the last point that is under development is the simulation of the phase contrast based on the speckle and grating techniques. Right now we have the propagation phase contrast, not the phase contrast that use this technique. So those are the main development that I will see in a CT simulation. So do you have a question also? Or the perspective of the CT simulation?
Yeah, we have a couple of questions here. I guess going back to your simulation and experimental images, one of the questions from the audience is, there were inclusions picked up from the experiment, but didn't pick up in the simulation. Can you comment on that?
Some inclusions, this thing, for example, or am I completely wrong?
I perhaps this one, yeah.
If this is that,
yes,
this is a defect on the scintillator. In the simulation, we don't simulate the defects on the scintillator,
okay.
at least yet. But yeah, on the experimental images, you will still have some defects like dust on synchrotron, as the setups are mounted, dismounted a lot of times. So you have dust behind the scintillator, dust inside the lenses. So yeah, and the scintillator are damaged. You have a lot of defects that you're not seeing in the simulation. This is true.
Yeah, thank you for that. And then there's one more question, and it's related to your last slide that you were on, and it's scatter photons simulation be useful for industrial CT where large metal parts and high X-ray energy causes a lot of scattering, and can we use it to train the network to correct the scattering of artifacts?
So yes, the scattering simulation will mostly be useful for such application where for large metal part, high X-ray energy, you can have like more than 10% of the signal which is coming from the scattered photon. So if you don't simulate that, you miss a lot of things. And training a neural network to correct the scattering, I think it's something feasible, because we did that for other artifacts. We have some promising results, so we'll for sure try it. And I think, yeah, it's something that can be done.
Okay, thank you.
No more questions here?
No questions.
Okay, so just to finish, I will briefly present the company NOVITOM, where I work. So NOVITOM is a small company. We are 18 people, mainly PhDs and engineers. This is a service company specialized in 3D imaging and chemical imaging, using advanced tools, like the synchrotron, as we already talked about. And we are also a software company, as we are selling NOVISIM, the CT simulation software. And we are also working on CT images analysis software, which will especially target the big image, the big image market, and high throughput analysis also. So this is it for NOVITOM. If you have also some question on NOVITOM, can respond to them.
There is a question in the Q&A. I don't know if we want to, for the sake of time, I guess we can answer it after the session is completed, Awen, if that's okay.
Okay. Okay. Yes.
Okay. Yeah, we have 1 minute, so let's try to wrap it up for everyone involved. I know audiences have other meetings as well. So this concludes our Ask the Expert series webinar. Thank you all for joining us today. Thank you, Awen, for this very informative session on NOVISEM and NOVITOM's capabilities and services. Regaku will be at USC later this month for a hybrid X-ray microcomputed tomography seminar and workshop. We're working with Earth Science Department over there, and very excited to have this collaboration with them in the next couple of weeks. That is going to be on September 27th. Please join us virtually or in person if you can. I've sent the registration link in the chat window, so feel free to register when you get a chance to take a look at it. Thank you again for sticking with us this year, and we look forward to new topics and new applications next year. Till then, take care and keep scanning.
Thank you,
Thanks,
everyone.
Thanks, everyone.
Bye.
Bye.